We propose a novel, low-cost speckle imaging technique that can measure micro 3D motions of multiple independently moving objects, such as fingers. Our hardware prototype has two basic components: a laser, which is defocused by a concave lens in order to illuminate the whole scene, and a lensless camera sensor. The laser produces coherent light, which interacts with objects in the scene to produce a high-frequency speckle pattern on the sensor, shown below. On the right is an image of the scene recorded by a conventional camera. We start by examining single object motion. On the left we see the scene recorded by a conventional camera. It consists of a small piece of chalk mounted to a linear translation stage. On the right is the same scene recorded by the CoLux sensor. Because the CoLux sensor is lensless, it captures only a speckle pattern. The scene itself is completely defocused. When the object moves, the speckle pattern shifts. Even when the object moves imperceptibly on the left, the speckle pattern shifts noticeably on the right. We exploit this motion magnification ability of speckle imaging for micromotion analysis. For the lateral motion shown here, the motion magnification ratio is about 60:1. For axial motion, which manifests as expansion or contraction of the speckle pattern, the magnification ratio is about 15:1. Here is an example of a more complex object motion. If there are multiple objects, each will produce their own speckle pattern, which is summed together in the image. Here we show an example with two objects. We can see that the two speckle patterns are superimposed and move independently. Here is another example with three objects. Three different moving speckle patterns are visible on the right. To measure the direction and magnitude of speckle motion, we compute the cross-correlation between consecutive image frames, which is a shifted delta function, as shown on the right. The location of the delta function's peak gives the amount and direction of speckle motion, from which we can measure the motion of objects in the scene. Axial object translation toward or away from the camera changes the scale of the speckle image. We can measure this scale change by computing the cross-correlation between image 1 and image 2 at different scales. The cross-correlation peak is largest when the scale of the speckle patterns in image 1 and image 2 match. By detecting the correct scales, we can estimate axial motion with high sensitivity, 10 to 15 times higher than existing methods. We emphasize that the proposed technique can achieve extreme motion sensitivity, but cannot track individual objects. Instead, it measures aggregate motion statistics of the scene, represented as a 3D motion histogram, shown on the right. Here we show a simple example of one object moving along the x-axis. The 3D motion histogram is computed over a sliding window of 15 frames. We observe from the 3D motion histogram that the object moves, on average, 40 microns every frame. The 3D motion histogram also captures axial motion along the z-axis. The true motion of the object is 40 microns per frame away from the camera. Here we observe an axial motion mode at z equals minus 40 microns. Note that a conventional camera cannot detect such small motions. CoLux's ability to detect multiple 3D micromotions makes it well suited for subtle micro-gesture recognition. We show proof-of-concept results on the 7 hand gestures shown here, consisting of single and multi-finger motions, which were chosen to highlight the capabilities of our system. Here we show a subtle finger gesture. If we toggle between two consecutive video frames, we can notice that the amount of hand motion is very small. It would be challenging, if not impossible, for a conventional computer vision system to detect such a subtle gesture. In contrast, CoLux is capable of detecting micromotions, shown on the right in the 3D motion histogram, at high frame rates. For the single pair of frames shown above, our system produces over 20 accurate gesture classification results, shown as a time series at lower left. Similarly, for a pair of frames for the vertical slide gesture, our system produces over 20 classification results, which allows it to disambiguate different similar micro-hand gestures. Here are a few more longer gesture sequences. In summary, our main contributions are a novel theoretical model and method for measuring micromotions of multiple independently moving objects, a novel Speckle motion analysis technique for recovering small motions along the axial direction, and conceptual design and hardware prototyping of a novel low-cost and high-speed micro-gesture recognition system with a potentially broad range of applications.